Yeah, it is good.
Okay, thank you. So, good evening, everyone. So, this is Dr. Peksha Agarwal, and I'm instructor at AI Shala, and I'm today going to explain about SVM, and I would like this talk to be more of an interactive one. So, if any one of you is having any doubts or anything, you can ask. And so SVM, so any one of you is having any idea about what SVM is and what does it do? What kind of learning method is it? So feel free to write in the chat box if you want to write something. Okay, and you can also ping me. So SVM. So let's start. So it's basically a supervised learning problem where you just in a supervised thing. What do we have is we have a classifier and we are given two classes, two or more number of classes, and we want to classify the data into one of these classes, right? Now, now when we are classifying it, so what's the difference between supervised and unsupervised? I hope you all know. So in supervised, we do have the labels to the classes. For example, suppose you have a basket full of apples and bananas, right? Now, if I say that there are some objects in the basket and some objects are having circular shape, they are red in color. If so, I define only features, and some objects are yellow in color and they are having lengthy shape. They are not circular in nature. So I have defined the features and I have not told what classes they are. So you have to classify it or you have to find out the similar objects. What you will do? You will uh, apply clustering or something, right? Just give me a second. Okay, so sorry for the interruption. So what happened? So I was telling about the supervised and unsupervised thing. So if I talk about let's say uh, uh, apples and bananas, and I have not told what these objects are. Okay, so I have told only features and I want them to classify according to the similarity. So that would be the clustering thing, right? So that is unsupervised problem. And what is a supervised problem? A supervised problem is where you have uh, uh, the set of classes and what those classes do. These classes are having you are already telling like these are the apples and these are the bananas. Okay, so you are already you have already defined the classes. So that is a supervised problem. You are telling that there are apples in the basket and there are bananas in the basket, and what is required is you just have to uh, uh, classify these apples and bananas correctly, right? So that is a supervised problem. I hope difference in the supervised and unsupervised is clear. So SVM is one of the supervised training algorithm. So I hope my screen is visible to you all.
The screen is visible.
Okay, okay. So yeah. So in SVM, what do we do is we just classify it such that classify the points,
Can
data
you make this
points.
full screen? Like, turn on the
Sorry,
slides. Turn
sorry.
on the slides. Slideshow view.
Okay, okay, okay. Sorry. Okay. Okay, this one, right?
Yeah, this is okay.
Okay, okay. Introduction to SVM. So support vector machines is a basically classifier supervised classification technique which classifies the data points into two different partitions. We will not talk about more than two right now. So we it classifies data points into two classes, and those two classes are, those two classes are separated by these support vectors. Okay, so let's start. So history of SVM. SVM is related to a statistical learning theory, and it was first introduced in 1992. SVM becomes popular because of its success in handwritten digit recognition. So it's a very old problem, but it's still in the use today. In today's scenario, also SVM works really well in certain cases, and I'm going to talk about what those special cases are. So guys, in today's lecture, you are going to see a lot of mathematics, and trust me that maths is not, it's very interesting one, and I'm going to tell like what are the things behind the maths. So I hope whatever, it's not one way, so you all can revert back to me, you all can communicate, so you can say if something is not quite clear to you. Okay, so SVM becomes popular because of its success in earlier 90s or so, and SVM is now regarded as important example of kernel. So I'm going to talk about kernel methods, and it looks a very heavy word, kernel. So you are going to have to do a lot of maths behind this, but actually it's a very very easy maths. I'm not going to say very easy, but yeah, if I'm going to give you guidance about it, then you will be able to understand what's going on. Okay, don't worry. Now, so this is example. So this is a classifier that classifies the green points and the red points. Now you can see there are two classes, and these two classes are linearly separable. What does linearly separable means? There is a linear line between those two classes. So I hope linearly separable word is clear, because I am going to use this linearly separable word a lot. Now linearly separable means, so SVM works on linearly separable data. Now, first point is it works on linearly separable data, and second case is it also works on non-linearly separable data, but there is again some lot of conditions about that. So, first of all, I'm going to discuss about linear SVM, where we have linearly separable data, and then second we are going to talk about the non-separable case, where we have non-separable data, as well as where we have non-linear classifier. What does that mean? Suppose there is a green point over here, and suppose there is a red point over here. So this is a non-separable case, because you cannot separate all the red points and all the green points. This is a red point, and this is a green point, suppose. So this is a non-separable case. But the figure right now shows, this figure right now shows separable case, right? So linearly separable case, linearly non-separable case. Then you have non-linearly separable case. What does that mean? Suppose you have classifier like this. Okay, this is the circular classifier, and all the red points are over here, and all the green points are over here. So this is non-linear classifier. Okay, I hope linear and non-linear classifier is clear, and separable and non-separable is also clear. So guys, you can ask if it's not clear to you. Any doubts up till now? I guess not. Okay, so linearly separable classes. Now let's see. So what do we see? That this is the equation of a line, right? This is the equation of a line. Y is equals to mx plus c, and m is the slope, and x is a x and y are the data points, right? So mx plus c, sorry, c is the intercept and m is the slope. So this is the line equation of the line, and it says that there are two classes. Suppose this is the +1 class and this is the -1 class. Okay, so line, so this points, this is the equation. So if this equation is less than equals to 0, so less than equals to 0, this point will be classified as -1 class. Otherwise, this would be classified as +1. So you just need to identify the line. This is the linear line. And what you want to do is you want to identify a linear line that classifies these 2 points. So SVM is nothing. You just want to find out support vector. This is called a support vector. One vector, which is a support. You just want to find out. I will not say this is a support vector because I'm going to discuss what a support vector is. And what I want to do is I want to find out a linear line that separates these 2 points. So up till now, I think this is clear that we want to separate the data points into two sets, and we want to find out the line. Now you can see there can be multiple lines. Now this line also separates these data points. This line also separates the data point. So what you want to do is you just want to you just want to estimate a function f. Okay, and that function or maybe classifier should have inputs. As input, x is the feature vectors, input data points, y is the output and predicted output, and you find out the difference between predicted and actual, and w and b are the weights and biases. Okay, so weight vector, data vector, and b is a bias. Okay, now you just want to find out a line between these 2 points. Okay, now this line can, how would you classify this data? So there can be multiple lines. This is one line, this is another line, right? There can be multiple lines, right? So how you will find out the which line is my classifier? How you will do that? So anyone, any suggestions? How you will? So our aim is, I hope the problem is clear. Problem is, you just want to classify the data points, and you have to find out a line. Now, which line would you select such that the that would be our best classifier? Now, suppose I select this line. This is one line. So what do you suggest? This is the good classifier or this is a good classifier? This is A and this is B. So A is a good classifier or B is a good classifier? Anyone?
B.
B is a good classifier, right? B is good classifier. Why? Because suppose a point lies over here, right? A does not classify this, but line number B, this line classifies this, right? This point which is near to this, right? So how do we select the line that classifies these two set of data points? Okay, so this is one classifier, this is one classifier, so there can be many multiple classifiers, right? This is one classifier, this is, so we say that this is not a good classifier. So but which one is a good decision boundary? So consider a two class linearly separable, this is very important, linearly separable classification problem, and there can be many decision boundaries. So there are different algorithms that have been proposed, and today what we are going to do is we are going to find out find out the best line using SVM. Okay. Now, out of this, which line would be fine? So, what actually we want to do is we want to. This is a bad decision boundary. Example of a bad decision boundary. Like this is a bad decision boundary. This is a bad decision boundary. Okay. Why? Because we want it to be in center, so that if there is some square point, it also this line also classifies this square point over here, right? So we want, actually what do we want is we want the distance between this point and this point to be maximum. Clear? We don't, because for this line this distance is small and this distance is very large. We don't want that. We want to maximize the distance. And right, maximize the distance out of all the distances. Which all distances? This distance from this line, this distance from this line, this distance. So distance from all the points, we want to take the minimum distances. Which one is having minimum? This point. Let me erase this one. And which one is having minimum distance? This point is having minimum, this point is having minimum distance, and this point is having minimum distance, and this, only these four are having minimum distance. Actually, out of this also, this is having minimum and this is having minimum distance, right? Out of all the distances from this point. And what do we want to do is, out of all the minimum distances, we want to maximize the distance from both the classes. Okay, so we want to increase this distance and we want to increase this distance, just decrease this distance. So we want to find optimal classifier that maximizes the margin from both the classes. So you are getting some idea where I'm going with this. So
Yes,
define a
yes.
margin. Okay. Okay, all right, great. So define the margin of a linear classifier as the width that the boundary could be increased by before hitting the data point. So what do we want to do is, we want to find out the line over here where the distance we can, which is at somewhere at the center. So that is maximized, right? So this line, actually you can see this distance and this distance is the maximum distance out of all the minimum distances. So which were the minimum distances? This one was the minimum distance, and this one was the minimum distance, and this one. Only these three were the minimum distances, right? And out of these minimum, what do we want to do is, we want to maximize. Suppose we have selected this line over here. So this distance would be less and this distance would be less, right? So we don't want to do that. We, what do we want to do is, we want to maximize that distance. So this is also called maximum margin classifier, right? So what do we want to do is, we want to find the maximum margin out of all the minimum points, minimum distance points. Okay, so if somewhere it's written like what is the maximum margin linear classifier, so that is linear SVM. And these two lines are called support vectors. This is called support vector and this is also called support vector. So this line and this line, these two are called as support vectors. So this support vector and this support vector over here, these two support vectors maximizes the width or maximizes the margin from the center point, center line. And which line is the, which line, that line which linearly separates the two sets of classes. Okay, this is called the linear SVM. This is the linear line, so we call it a linear SVM. Suppose this is the line and we maximize the distance over here and over here, and there are certain points inside it and there are some points outside it. Okay, so this is the non-linear classifier. Okay, so this is a non-linear classifier, this is a linear classifier. So what we are studying over here is linear SVM. Okay, now, so these two, this one is called support vector and this point is, again, defines the support vector, are those data points that the margin pushes up against. And these two, this line, this one is, and this one is called support vector. Basically this and this, the distance from the center to the this point, this is the support vectors. Okay, and this is the simplest kind of SVM, which is called the linear SVM. Simplest, this is the simplest one because we are going into complex maths next. And this is the simplest one. Okay. Now, why maximum margin? Because we want to maximize the distance between the class number 1 and class number 2. Okay. This is the plus one and one class, and this is minus one class. Okay. Two types of classes. Now consider this example. Now suppose you have example, so I will draw this example and you can relate it. Okay, suppose this is the line. If you put x is equals to 0, what you will get, you can tell me. If you put x is equals to 0, x equals to 0, you will get y is equals to
9.
9, right? No, minus 9.
-9.
Y is equals to minus 9, right? So this is x is equals to 0 and y is equals to minus 9 over here like this. So this point, right? Sorry, minus 9 would be somewhere here down, right? Somewhere here. And suppose you put x, y is equals to 0, what you will get? 9 divided by zero point 0.4, something like that, right? So this example actually is 0.4x minus y minus 9. So actually this line is somewhere here. Okay, this line is actually somewhere here. Now what do we want to do is, if I put w value of w, so this is the mx plus c, this is my m, this is my m, and this is my minus 1 is right over here. Okay, and this is b, right? These are my weights and biases, weights and biases, and this is x and this is y. Okay, now 1 comma 3, suppose I put 1 comma 3 in this value, I will get is 5.6. So 1 comma 3 point is somewhere here. Okay, so I will get 5.6. If 3 comma 5 is somewhere here, so I will get somewhere here like this point, I will get 2.8. 5 comma 7, so this is the line over here, so I will get 0, and this is the point 7 comma 9, I will get somewhere here. So you can see that as I keep on increasing the x and y values, I will get a negative value of this whole line. Okay, and if I decrease it, I will get the positive value. So this is plus 1 class and this is minus 1 class, and this is the line. And if I keep up, if I get a point over here, so that value I will get 0, right? So every point that satisfies that line, I will get 0, and if a point is below the line, I will get plus 1, and if a point is above the line, I will get minus 1. That is why we classify svm classes into plus 1 and minus 1. We don't use 0 and 1. So if you have suppose a data set where you have zeros and ones, classes as 0 and 1, you convert it into plus 1 and minus 1 always. Why? Because 0 means we are finding the points that lie on the line. No, we are not doing that. We are finding out the points that are above the line and that are below the line. So points above the line you will get minus 1, and for the points below the line you will get plus 1. So I hope this thing is clear. So from now on, I will not going to discuss like classes 0 and 1. I will say like minus 1 and plus 1. Okay, two classes are there, minus 1 and plus 1. Okay, so if you get a data set where you have labels 0 and 1, you convert it into minus 1 and plus 1 in the SVM. Okay, now let's start with the maximum margin formalization. Now, classifier. Now, there are two types of margin. One is the functional margin. Functional margin of the data set is twice the minimum functional margin for any point. 2 comes from twice. Why this is functional? Actually, if you see over here, so this is the margin, right? This plus this, right? Okay. So this plus this, right? So these two are the basically distances. Okay, So this is called a functional margin. Okay, so functional margin equation is this. You can also simultaneously note it down. So this is the equation of the functional margin, yi wt xi plus b. Okay, functional margin is this, right? This is the equation of the functional margin. Now, functional margin of the data set is twice the minimum functional margin for any point. Now, twice because you want to maximize the distances over both the sides. So this is the equation of the line multiplied by some yi. So this is the equation of the, whenever you someone says what is the functional margin of xi of any point, so you will say this is the functional margin. Okay. Now, second is the, now the, what is this functional margin, and what is the problem with this functional margin? So this is a functional margin, but the problem is, suppose as I keep on increasing the vectors, suppose I make new support vectors over here, now this distance would increase. Okay, so suppose equation of this was wx plus b equals to 0, and equation of this would be wx plus b plus 1, and if you keep on increasing it would be plus 2, and if you keep on increasing this plus 3. Okay, so function margin depends upon the width of the, what do you call, width of the support vectors or the distance. So getting what I'm trying to say over here, so this is 9. So 9 is, suppose I want to do make a line, so I will, instead of 0 this would become 1, instead of uh, uh, as I keep on increasing this width, if for this distance, right, this distance support vector distance would, this would become 2, and as I keep on increasing this functional margin, so this is depending upon the width of the support vectors around this line, right? So this is the main line, and then around this one support vector and another support vector, and functional margin depends upon the width. So what do I want to do? I want to normalize it, right? Why do I want to normalize it? Because I don't want, suppose vectors, I don't want the, suppose data points were here and here, I don't want this and this to become like my functional margin, right? I want it to reduce, I want the equations to get reduced, right? So what I want to do is I want to normalize it. And how would I normalize it? If I divide it by w, right? If I divide it by width, right? If I divide it by w, it will get normalized, and that is called the geometric margin. So this functional margin is basically scale variant. As scale gets increased, margin varies, margin changes. As you increase the scale, margin changes. So this is the issue. So what we do want to do is we want to normalize it. So we divide it by w over here. So this was a functional margin. Now we divide it by W and we get a geometric margin, right? Now, equation, now examples closest to hyperplanes are support vectors. Now, this is a support vector and this is also a support vector, and this is the margin, rho. This is represented by rho. Okay, rho represents the distance, actually the margin between these support vectors. Okay, so our aim is to margin, find out the margin p of the separator, which is the width of the separation between support vectors of the classes. So this is the support vector and this is the support vector, and what do we want to do is we want to maximize this margin. So you can see this is a optimization problem. What do we want to do is we want to maximize the margin, right? We want to maximize the margin, uh, which should be scale invariant, and that's why we divide it by the w, right? Now this was the equation. This was the equation for positive class, and this was for the negative class for the support vector. This is not the equation of the line. Equation of line was this. And if I say it is greater than 1, the points is above the line, and if it's less than 1, points were below the line. That's what was the case was in this example we have seen. If point is above the line, it's classified as a negative point, right? So if point was, sorry, this is the minus one. So this is minus one and this is plus one. So this is the equation of these two lines. This one, line number one and line number two. Okay, so these two vectors, basically line of this one is wtx plus b greater than equals to 1 and minus 1. So all the points that are above this line are classified as negative points, and all the points that are below this line are classified as positive points. I hope up till now everything is clear.
Yes, ma'am.
Okay, great. So I'm trying to make it as simple as possible because from now on we want to move to more maths. Okay, now. So we want to, yes,
Still like confused on the maximization part. Like, why exactly are we doing it?
exactly what we want to do is, you will tell me like what do we want to do. We want to find out these values of w and b, or we want to find out this line number 1 and line number 2 such that it maximizes this margin, right?
Hmm.
That's what we want to do, right? So we want to
Oh,
find the equations of this line and this line.
okay, okay.
And how do we find out the equations? When we get the values of w's and b.
And B?
Okay, so we just
Yeah.
want to find out w and b, and plus we want to maximize this margin. This margin is 2 by w, 2 times the width, right? 2 times, and we are normalizing it with the width. We are normalizing it with w, right?
Hmm.
Okay, now uh, so this is the basically hyperplane. Actually, when we want to talk about two dimensional, so it is a line, and when I'm talking about three dimension, it's a plane, and when I'm talking about four dimension, it's a 3D plane. And you can imagine it because I'm talking about 2D. So 2D, it's a line that separates these two. So that's what a hyperplane is. When I'm talking about 3D, it's a 2D plane that separates between these two points, set of points. Suppose this was 3D, so there is a plane over here, right? That separates these two points. Now, suppose it's in a 4D. So as dimensions keep on increasing, so you will find a hyperplane. Okay, and what hyperplane now? Actually, what are these dimensions? Dimensions are nothing. It's just the features of the data set. Suppose you have 2D data set. 2D data set, how does it looks? You just have one x and one y, one x and one y. So this is a simple 2D data set. Now, if you have a 3D data set, what does that mean? 3D means you have two x, x1, x2, and y. So you, what you will want to find is 2D plane. You want to find out a 2D plane that separates the points into classes, different classes, into +1 classes and into -1 classes, right? Now, if you have 3D, 4D data points, 4D data points means three features and one class. And you, what do you want to find out is you want to find a hyperplane. Hyperplane means equation. So what does, how does this equation changes? So you need to see that equation would be w1 x1 plus w2 x2 plus w3 x3, where x1, x2, x3 are feature vectors. Okay, plus b greater than 1 and less than 1. So these two equations would be there, and you want to find out w1, w2, w3, and b. Can you imagine the hyperplane that separates these two set of points? Okay, so it's difficult to show it over here, but I hope you are getting the point. I would erase this one so that underlying things are getting clear to you. Now, so this is the WTX plus B equation. What we want to find out is this equation minus 1 and the second equation plus 1. Okay, and for 2D, it would be W1x1 plus W2x2 plus V for 3D and so on. Okay, so for multiple dimensions, what you want to do is you want to maximize this P, or I will call it rho. So you want to maximize this rho variable, and what you want to do is you want to find out these two lines. Okay, now mathematical equation. Now from now on, mathematical things are starting. No need to get confused. It's very simple. What you want to do is you want to maximize this margin given two conditions. First condition is this and second condition is this. And what are these two? These are the equations of the lines. And what you want to do is you want to find out the equations of these lines, this line and this line, right? Now, if I say I can convert a maximization problem into a minimization problem, right? Because maximizing is a different thing and minimizing is a bit easier, right? Suppose there is a problem, I would say, and find out there is a function, convex function, and I want to maximize this. So it will be infinite, value is infinite. It can maximize a point is this for the function, for this convex function. Minimum point is this, right? So minimizing is easier, right? So what we want to do is we want to convert the maximization problem to a minimization problem, right? So instead of maximizing 2 by W, I will minimize W by 2. So that's what W by 2 is over here. And if I'm minimizing W by 2, I can also minimize W square by 2. So this is nothing. This is just W square by 2. This thing is clear. So in books, you will see this equation, minimizing equation. Why? Because we don't want to maximize anything. We want to minimize it. So instead of maximizing 2 by W, what I will do is I will minimize W by 2. And instead of minimizing W by 2, what I will do is I will minimize W square by 2, which is WTW by 2. Okay. And remaining equation remains the same. Up till I think there's no confusion up till now.
What is the requirement of squaring that time for minimizing?
Yes, nothing, no requirement. You can also do it by W by 2. But the problem is you want to make calculations easier, simpler and easier.
Thank you.
Okay. Now, now I will just go back to your 10th and 12th class where you would do the optimization. So have you studied optimization? So optimization is a different complete subject in a mathematical class where they tell you about constrained and non-constrained optimization problems. So there are two types of optimization problems. So if you have no idea about maths, so I have a book. So you can just read that book. So I have downloaded it somewhere. I don't know where is it. Okay, this is the book. Book name is Data Mining Concepts by Vipin Kumar. So in the back end, you will find the two things: constrained optimization and non-constrained optimization. So what is a constrained optimization? I will tell you just basic. I will not get into the maths behind it. I will tell you in simple terms. What does it do is, suppose I have to find out the suppose maximum of this function. So finding out maximum of this function is infinite, right? Infinity points are there, and it can maximize up to a certain point. Now I will apply constraint. This is the constraint. I will say between 1, x is equals to 1 and x is equals to 2 only, you have to find out the maximum. So you would say, okay, this point is the maximum point and this point is the maximum point, right? This is clear. So what is constraint? You are putting constraints on your function that in between those constraints you have to find out maximum value or minimum value of the complete function. So this is nothing, this is just a function, right? This is a parabola function, simple function. And what you want to do is you want to find out, suppose minimize or maximize this function, and between point 1 and point 2 you will say this is the maximum point and this is the minimum point between the function, right? So this is called a constrained optimization. Now to solve the constrained optimization, there are two things you have to just get an idea about, because it's a bit complicated maths, but I will not get into it, but I will explain it into very simple terms. Now first thing is equality constraints. Constraint optimization. Now I hope this is clear. Constraint and without constraint. So I am going to get into constraint optimization, and then in constraint you have two things: equality constraints and then non inequality constraint. Two things are there. Okay. So I will also say it is of two types. One is equality with equality, and other is without equality. Okay. Now let's see how we will solve it, because this is the optimization problem we have got in the SVM, and how we are going to solve it, let's see. So first thing is first basics. How do we solve a constraint optimization problem? How do we do that? Okay, so how do we do that is we first of all find out equality. Let's see equality constraint. What is the equality constraint? Suppose we have a function fx1. I hope my screen is visible.
Yes, the PDF is visible.
Okay, yes. So this is the equality constraint. So if you have a function f, okay, and constraint is this one. Okay, so this was a function. I have shown you parabola. So this is, suppose this is a parabola. This is a function of parabola, maybe circle or something. And constraints I have put like x is equals to 1 and x equal to 2. X should lie, x is equals to 1, or x should lie in between that. X equal to 1 and x equal to 2. So I put some constraint where this term is equal, gx equal to 0. Okay, equality constraint. Now in inequality constraint, you have hx less than equals to 0. I say for all the points that are less than equals to this line. Okay, so that is the inequality constraint. Now for different types of constraints, you have different type of equations, and there are different types of conditions that you apply to solve it. So for equality constraint, what you do is, for equality constraint, what do? You use Lagrange multiplier to solve this function fx. Okay, to solve fx, what you do is you apply Lagrange. And what is Lagrange? This lambda, this L, Lx lambda is the Lagrangian function, and what it does is you just change this fx to fx plus lambda gi for all the gi's. Okay, so what you do is you apply lambda some, and then finally what you do is you derivate this equation with respect to all the x and all the lambda and put it to 0 and solve all the equations. Okay, simple method. You just put a lambda fx plus lambda gx, and then derivate the whole fx plus lambda gx with respect to all the x's and all the lambdas. Okay, and then once you do it, find out the value of x and find out the value of, so this is the simplest method. And why you are doing this? You just want to minimize this function. Minimize this function means find out the value of x that has the minimum value for this function. Okay, I hope this thing is clear what we are doing right now. Any doubts? It's clear. Okay, great. So what we want to do is we just want to minimize the function fx, and we want to find out x that has a minimum value for this function fx. Okay. Now, for solving this, what we will do is we just put lambda gx fx plus lambda gx. What is gx? Gx is the constraint. X is equals to 2, x minus 2 equal to 0. Equality constraint example, right? So lambda gx, and then what we will do is the whole equation, take the whole equation and derivate it using x's for all the x's and for all the lambdas. So example is, suppose it's a function fx plus 2y. Fxy is equals to x plus 2y, and constraint was x square plus y square minus 4 equal to 0. Equality constraint is there. Okay. So function is there and equality constraint is there. Now what you want to do is you just want to derivate it. You put fx plus lambda gx, okay, fx plus lambda gx, and what you will do is you derivate this with respect to all x and all lambda. Lambda l derivated with respect to x, delta l by delta x, delta l by delta y, and delta l by delta lambda, and put it to 0 and solve these three equations. Three variables, three equations, you can solve it. You get x is equals to minus 2.5 and y is equals to minus 4 by root 5. So this is the solution. So at this x comma y point, this function, which function, x plus 2y, is having the minimum value for this constraint. I hope this example is clear.
Yes, it is clear.
Okay. Okay. So next is inequality constraint. Similarly, we have done for equality. Similarly, we can do for inequality. So inequality function is hix less than equals to 0. What we will do is we put fx plus lambda hx, fx plus lambda hx over here, and it is solved. That was solved using Lagrangian, right? Lagrangian. This is solved using KKT, Karish-Kandekar equations. This is very important equations for optimization of a inequality constraint problem. So what you will do is you will apply KKT conditions. And there are four conditions that you must remember for solving this kind of equation. So first equation is exactly the same. You just derivate it with respect to all x and y's and you get 0. This is the first that you already do in Lagrangian. Exactly same. Okay. Here what you will also extra work, you just put the hx2 less than equals to 0, lambda I greater than equal to 0, and lambda I hix equal to 0. So these three are equations, and you will get set of equations after performing this. And then what you will do is you will find out the values of x and lambdas and solve the equation. Example is given over here. So this was the less than equal to y greater than. So these two are inequality constraints, and this is the function f, and these are the equations. And now what you will do is you will solve these equations. Okay, how you will solve these equations? You will start solving from lambdas, lambda 1, lambda 2. Okay, you start solving from here. You put lambda 1, lambda 2 equal to 0. If you put these two equal to 0, then what would be the case? If you put either one of the lambda 1 equal to 0, lambda 2 not equal to 0, then what would be the case? And so on. You will solve the equation, and finally you get x is equals to 0, y equal to 2, and this is your answer for this question. Question was, you have to minimize this function for these two inequality constraints. So x is equals to 0 and y equal to 2. This at this point xy, you will get the minimum value for this function. I hope the KKT conditions and optimization is clear. So this is the basic maths. Okay, all right. I hope, I know it's a bit complicated thing. Similarly, so let's go back to SVM. So at SVM, what we want to do is we want to minimize this function. Now you have to tell me this is equality constraint or inequality constraint. So we will apply Lagrangian or KKT over here. This is our optimization problem. So anyone? Uh, guys, you're getting what I'm talking about, because I get it, it's a bit difficult to understand in one go, but if you are getting it somewhat, then I hope then you are going to, when you are going to read it by yourself, you will get it word by word. Okay, let's go back. What we want to do is we want to solve the SVM, and we want to find out the support vectors, and we want to find out two equations of the line that maximizes the margin, this margin, and we have converted it into minimization problem, and we want to minimize this margin, and constraint is because it's greater than equal to, this is a constraint, and greater than equal to means it will be solved by inequality constraints. With equality will be solved by simple Lagrangian, and without equality will be solved by KKT, which is Kharshkund-Tucker problem that we have seen example right now. So we will use the KKT to solve this, and this is our problem. And how we are going to solve this is we apply the Lagrangian. We apply the Lagrangian to the function, and after applying the Lagrangian and derivating all the W's and B's, all the W's and B's, put it to 0, and when we solve it, this is the final equation that we get. So this is our final equation when we apply Lagrangian to this, and after solving it, this is our main function, this one. This is the solution for the optimization problem that we have seen right now. Okay, now uh, whenever someone asks you what is the solution, so this is the final solution. So this is how values of W are calculated, and this is how B is calculated. Okay, so using these two equations, you can calculate W and B, and you can find out the two support vectors that you want to find out for best with the maximum margin in the from the data set. Okay, now that was a separable case where the points were completely separable, right? Here in the non-separable case, one point, suppose this is the class 0, uh, let's say over above, this is the class -1, and this is the class 1. Okay, now this cross is over here and 0 is over here. Now it is non-separable, because suppose 0 was over here, you cannot draw a line that separates these 2 points, right? Because you are having this class variable over here and this class variable over here, so it's a non-separable case. In non-separable case, there is a slack variable. Okay, slack variable is added to the equation, because you can see this blue point lies inside the red point. So no matter how you draw the linear boundary, this blue point will always be on the left side, and this red point will always be in the right side, no matter how you draw this line. This line, any line would never classify this point. So what is a slack variable? We add a slack variable, and what we want to do is we want to minimize training set and place plane far from each class. Basically, what we want to do is we want to minimize this error. This is the error, and we want to minimize it. So in addition to, I would say this one, if I erase this, okay, so what do we want to do is we want to minimize this error, because this is the error, this point is the error, right? This 0 is the error, and here this blue point is the error, right? So we want to, what we want to do is, in addition to this distance, we also want to add this distance, right? And we want to minimize it. Okay, so this is a new function where what we want to do is we want to add this slack variable over this. So new formulation where the points are non-separable, this is the new formulation. Okay, and how do we solve it? Again, we use the KKT. Okay, and we put it to 0, and finally we get something like this. Okay, we solve the equations and we get apply Lagrangian and solve the equations and use a this is also called soft margin, because you have some points, plus points on the negative side and minus points on the plus side. Okay, so that's a soft margin. Okay, so this is the all about the classification. Now I hope the point is clear. So what we want to do is, this is a summary separating it into hyperplane, and this is the final set of equations that you get if you solve it, okay, using uh, uh, SVMs. Okay, now there is linear, non-linear SVM. So this was the linear SVM. Suppose this is a point, this one and this one, and you just separate it out. Okay, now suppose this is the data set where you have uh, 4 red points, 3 blue points, and then 3 red points. Okay, and suppose you draw a boundary like this, then also these 2 points are not getting separated. You can see that red points, 50% of red points are on the right side. So this is not a good decision boundary. What you do is you change the dimension it to 2D. When you draw this 1D diagram to 2D, when you convert it into higher dimensional space, these points, the distance between points increases. Why it's happening? Suppose this was the point, there was a distance 1 and 1 between these two, and if you change it to 2D, you will get a point somewhere here like this. Okay, so the distances between points increases if you convert this 1D to 2D. Now you can classify it easily. Okay, so this, you can see this data set is converted into this when you change the dimensions of the data set. So for non-linear SVM, what we want to do is we want to change the dimension, and how we want to do is we use kernels for it. Okay, so non-linear SVM, what we want to do is we want to change the dimensions, okay, and change the feature spaces, and then find a hyperplane that classifies these 2 points into, so all the red points are below this hyperplane and blue points are above this hyperplane. Okay, so we want to, so this is a non-linear boundary, and how we converted it, we use kernel function, and kernel function changes the dimensions 2D to 3D and finds out the hyperplane which can separate these 2 points. Okay, so this is the kernel trick. What does kernel do? Kernel function is some function that corresponds to inner product of some expanded feature space. Basically, it changes the feature space and it converts the original function, 2D function to 3D function maybe, and then finds out the hyperplane that can separate these 2 points. Okay, so this is a kernel trick. So when you use kernel, so there is again optimization using kernels. So now you optimize this function instead of that function, and final solution you will get something like that. Examples of a kernel function is, suppose you apply this polynomial kernel function, so you have to use this equation. You apply RBF, so you have to use this equation, and so on. So basically kernel is nothing, you are just changing the dimensions. So you can apply this function also as a kernel, and you will change the x1, x2 to z1, z2, z3. So 2D to 3D you are converting, and you are just finding out the best possible solution. Okay, so that's all about the SVM. So I hope I'm able to explain what the SVM is. And this is used over this data set. You can search this data set online. This was applied on this much categories and for these tokens, and this was very prominent solution. You can search it online and you will find this data set and solution online. So this was applied on the used for SVM. Now you can use recall, precision, and accuracy measures for classification. And I hope you know this, what is recall, what is the precision, and what is accuracy. If you know it, then I'm going to skip this part. Otherwise, I can explain this as well. So we just want to find out the whenever we are classifying predicted by we are predicting some class and there was actual class. Suppose we predicted +1 and actual was -1. So this is the error. and we calculate the error for all the examples, and then we find out the accuracy. So this is how precision and recall is also calculated. Okay, so then macro and micro averages, similarly again some few formulas, and then you can calculate it. So that's all. And this is the ROC curve. We just want to maximize the area between this curve, and if this is the maximum, then the algorithm works great. Okay, so that's all about the data set. Now if you have very few data set, then you can use algorithms like navy base. But if you have the reasonable amount of data set, you can use svm or other clever classifiers. So that's all about the theoretical part. Now because we are having short of time, I guess I'm going to just quickly go to the I have done some code with for you guys. So this is the support vector machine code in Python. I hope my screen is still visible to you all.
Yes, yes.
Okay. So this is the data set. I can show this data set to you. Okay. So let's plot this data set. Suppose this is the so I've imported book9 .csv file, and it was having several points. So let me show this to you. This data set I have. This is the data set. Okay, this is the data set. You have user ID and whether it's he or she is male or female, then gender, age. Sorry, actually this is like this. Okay, so gender and then age and then estimated salary, and then you have whether he has purchased a car or not. Okay, so this is the thing that we are having. Now I'm going to select few columns from this to predict whether he has purchased or not. So 0 or 1 classes are there. I will consider this as -1 and this is +1, and this is the features. So these all are actually features. So I have taken this one and this one as input, and this is the purchase one. Okay, now let's have a look at the code. Okay, so this is the x array. If I print it out, so this is the 19 and 19,000, which is x and which is y. Actually this is the age and this is the estimated salary. Okay, x and y. Actually I have taken this one. Okay, now what I want to do is, so I have used numpy. Numpy is used for numerical computing, and I have imported this as NP. Matplotlib is again Python package for plotting the graphs and all. And pandas is again working with the data frames and all. Now what I want to do is I have imported pd.read CSV. I'm reading the CSV book9 CSV. Click this and then I have clicked this. Okay, I have imported this from here, and this is book9.csv. Okay, now x is equals to datasets.ilo, and values basically columns are selected, and then again y columns are selected. And from the sklearn, I hope you know, it's again the Python library for, you will get so many models, already built-in models in the sklearn. So I have split the data set into 75% training and 25% testing. So X train, X test, Y train, and Y test. So I have splitted the data set, and I have sklearn.import standard scaler. Basically, I want to scale the X features. Scaling means I want to change the values because it ranged from 0 to 25,000. So I want to scale it. Okay. So I have used a standard scaler to some range, maybe some normalized value. So if I plot this, if I print it, you can see the scale value. This is the original X values. If I print it, suppose I print X train. So you will see it like this. So this is the normalized values, because I don't want to train my data set on this large value. So what I have done is I have normalized the x. So why do we do normalization? Is because we want to make algorithm learn faster. Okay. So why predict is classified SVC. From sklearn.svm we have simple support vector classifier which is linear type. So I can import kernel function which is polynomial, which is maybe Gaussian function. So many functions I can import, but because my classifier I want to use is linear, so I can use linear. Random state is 0 and classifier dot fit. I have fitted the model over here. Now as soon as I do classifier dot fit, I will get my SVM will start running and it will fit the classifier. Now I will predict the y predict. So you can see the y predict values and y test values. If I want to see that y, oh, so sorry, actually the name is this one, y predict. You can see, so this is the this is the test values, okay, and this is the predicted values. Okay, so the difference between these two is plotted as what you'll call the confusion matrix. Okay, and then what we have done is we have just, this is just the matplotlib. I just wanted to visualize it very colorfully. So this is the SVM training set and this is the test set. You can see for the test set also it is classifying most of the green boundaries as green and red as the red. So it's working really good. Okay, this is the training data set and this is the testing data set. So this is the final answer. uh, I hope so. That was all about the SVM. I hope I'm able to um, uh, explain what I want to. So that's all from my side. So if you have any questions you can ask.
Ma'am,
Yes.
when is the homework assignment getting released?
Sorry.
When is the assignment getting released?
Assignment, I think I'm not the right person, so Sabya maybe can answer this.
Okay, okay.
Okay,
Also, the assignment, like, is it like based on the maths we did or just the concepts?
okay, you have to complete some assignments. You will be given that,
Yeah.
like you will be having Google Forms. You will have MCQ questions, and maybe you have to write 2 or 3 lines question answer also.
Okay. Like, one more question. Like, is the assignment like based on the maths or like the concepts we learned?
It will be mixed based on maths, logics, logical reasoning, everything.
Okay, got it.
Okay, any other questions from anyone?